Hello, my name is Chris Harris and I'm from Alloy Chemistry, and welcome to this video on hydroxy compounds. This is topic 16 for the CIE specification, so that's the Cambridge Internationals. In this video, obviously, we're going to be looking at hydroxy compounds. That's the ones with the OH group in there and all the various reactions that go along with it. This video is just one of a series of videos for CIE that covers the full A-level specification. You can find them on Alloy Chemistry YouTube channel. Please hit the subscribe button. That'll be massively helpful just to show your support. All these videos as well, these are actually slides which you can purchase to supplement your revision. They're really good value for money. I've bunched them up in terms of topic 16 will fit within the full organic chemistry subtopic for year 1, but the full range of year 1 and year 2 is there as well. So if you just click on the link in the description box below, and you'll be able to get a hold of them there. So like I say, they're good to kind of supplement what you've already got, your notes and other revision books as well. So let's get into this topic and let's see what this is all about. Now, what you'll probably find is a lot of the CIE topics kind of overlap themselves. So what's best is to kind of make sure you've got a good understanding of the previous topics first before you actually go on to this topic. The key thing is to have that understanding. There's bits in here which I will go through that you might have seen in previous topics, but I'll put it mainly in the context to obviously the hydroxy compounds topic, so alcohols, etc. But so you will see there's a little bit of overlap on here. You haven't got any deja vu or anything like that. So I'll try and bridge where I can as well. I'll kind of refer to other topics if I think that's going to be useful. Right, so let's start with this bit first. So hydroxys, like I say, is basically the OH group, and one of the obviously the common molecule with the OH group in are alcohols. So let's have a look and see what an alcohol is, or look at an introduction to alcohols anyway. So alcohols, like I say, have the OH group, hydroxy or hydroxyl, sometimes it's also known as, that's its homologous series. And the general formula for alcohols is CnH2n plus 1 OH. So that's the general formula for it. You've got different types of alcohols, and you would have seen probably from the previous topics of halogenoalkanes, and you would have seen a little bit in the alkenes and alkanes topic about primary, secondaries, and tertiaries. It's exactly the same for alcohols as well. No difference here. So alcohols, again, the same principle applies with alcohols. You have your OH group, your hydroxyl group, bonded to a carbon, which is bonded to one other carbon. That's classed as a primary alcohol. So an example would be butan-1-ol. Secondary alcohols is where the hydroxyl group is bonded to the carbon, which is bonded to two other carbons. That's a secondary alcohol, so that would be butan-2-ol. Tertiary alcohols is basically where the hydroxyl group is bonded to the carbon, which is then bonded to three other carbons, is a tertiary alcohol. So an example of that would be 2-methyl-propan-2-ol. So make sure you're aware of what the primary, secondary and tertiaries are. These will become a little bit more important, particularly when we look at oxidation and reduction of these chemicals here. So we'll come onto that in a minute. Okay, so let's have a look and see how we can make chloroalkanes. Now, this is linked with the halogenoalkanes topic, which is topic 15. So there's a bit of an overlap here. But so if you've seen that topic, you'll know exactly what a chloroalkane is, basically. But they can be made by reacting an alcohol with various different substances, and so we need to be aware of what these substances are. So, for example, we can use phosphorus pentachloride, which is PCl5, to react PCl5 with the alcohol. It could be any alcohol like methanol, ethanol, etc. And what you'll form is your alkyl chloride, so your chloroalkane, should I say, which is this here. You'll form some HCl, and you'll also form POCl3 as well. So this is your chloroalkane, and this is basically how you can use phosphorus pentachloride to make that from an alcohol. We can use hydrochloric acid as well to do the same. Again, there's our alcohol there, reacting it with HCl. and we form our chloroalkane, which is here, and water we produce. So there's a couple of ways in which you could do that. So let's have a look at an example. So for example, we can react 2-methyl-propan-2-ol to make the halogenoalkane 2-chloro-2-methyl-propane. Okay, so here's an example here. So there's your 2-methyl-propan-2-ol, which is this one here. So this is your tertiary alcohol plus HCl, and that will make your tertiary halogenoalkane plus water. So it just kind of shows you kind of how that's made as an example. And obviously this 2-chloro-2-methyl-propane, this one here, can be purified as well further via distillation, so you can remove any other impurities from that, including water. So tertiary alcohols, they react the fastest with hydrochloric acid and the slowest with primary alcohols. So tertiary alcohols are more reactive when you're reacting them with hydrochloric acid. So if you're looking for a rapid reaction, then use it with tertiary. Okay, so how do you make bromoalkanes then? So haloalkanes are made from alcohols via substitution reactions. So obviously we've seen some of these before with regards to the alkanes, the haloalkanes topic. So this is just obviously focusing on the alcohol side, as I say. So a haloalkane is made when an alcohol is reacted with a halide ion. So that could be, for example, Br-, and you normally get Br- ions from, say, sodium bromide or something like that. It's a ready supply Br- ions. And we use an acid catalyst, so we normally use a 50% concentration of sulfuric acid to get this reaction to go. So let's have a look. So initially, we've got the sodium bromide reacts with sulfuric acid, so H2SO4. So that's your catalyst, to form hydrogen bromide first. So that's the first reaction. So there's your hydrogen bromide. It's really difficult to get this on its own. So you have to, obviously this is a solid. We can store this in a cupboard quite readily. So normally to make other products, we normally have to do a pre-reaction first. So it's like preparation for it. So we use the sulfuric acid to form HBr. And then it's the HBr that reacts with the, in this case, secondary alcohol, which is here, to form your 2-bromobutane, which is this reaction here, and you obviously for this product here, and you form water as well. So this is just a reaction where we form an alcohol. Just remember that little bit there, though. Okay, the role that the catalyst plays to form the HBr in the first place, and then obviously forming your haloalkane or your halogenoalkane. And obviously this is a substitution reaction because we're swapping the alcohol for the bromo. So the bromine which is attached to the molecule. Okay, so how do you make iodoalkanes? So we're kind of going through the whole series here. So you've got chlorine, then bromine, then iodine. Iodoalkanes are made by reacting an alcohol, again, that's the common theme, with Pi3. So this is phosphorus triiodide. So you've got your alcohol here, reactant with phosphorus triiodide, and that forms your iodoalkane, as you can see there. And we form H3PO3 as well. So this would be quite acidic. This actually forms an acid. So the Pi3 is actually made in situ under reflux. So that means it's made at the same time with the alcohol and red phosphorus and iodine. So basically you kind of throw all this into one vessel, and the Pi3 is actually made. You're not actually adding Pi3 in. Basically, you're adding in red phosphorus into that and iodine. So you're mixing these two chemicals together with the alcohol in reflux, and then these two will react together to form the Pi3. So that's what means in situ means. Obviously, it's just made all at once, which is nice. It's like one pot cookery. So yeah, so that's good. Now red phosphorus, like I say, it's just a type of phosphorus. You get many different versions of phosphorus. So red phosphorus is obviously added in here. It's similar to carbon. Obviously, it comes in different what we call allotropes, which you will have seen in a previous topic. And basically, red phosphorus is the type of phosphorus that's found on the end of matches. So obviously you've got to be careful with this, because obviously if you strike that against a rough surface, it spontaneously ignites. So yeah, you've got to handle that with care. So normally you take your red phosphorus, mix that with some iodine with the alcohol under reflux, and then you should get your iodoalkane from that. So yes, very straightforward. Yeah, you don't literally have to scrape the edges of the matches off to get your red phosphorus. It does actually exist in containers, which is useful. So another reaction of alcohols is dehydration of alcohols. So you'll see a lot of these are just, here's an alcohol, what can you do with it? A bit like an ingredient in cooking. So you might have an onion, and you'll say, right, well, what can you make with the onion? You can make loads of different things with onions. You'll find that a lot of the CIE topics kind of follow that same theme, where they'll say, right, here's an alcohol. What reactions can you do with an alcohol? What things can you make from it? So it's quite versatile, and I quite like the way they kind of go through these, because they kind of go through the different reactions. So this is another one anyway, which is dehydration of alcohols. So dehydration is basically where you remove water. It doesn't, there's no special term for that really. So just as you would probably hear in everyday language, and basically we can make an alkene by dehydrating the alcohol. So we can eliminate water from an alcohol to produce an alkene, and this is because obviously we're removing water from it. So this reaction actually involves the use of an acid catalyst, and you can either use sulfuric or phosphoric acid. So relatively straightforward reaction, to be honest. It's just ethanol, and we remove water and you form ethene, which is your alkene, and water vapor. So basically you're dehydrating the alcohol. Now, alkenes are mainly used to make polymers, so it's obviously got a really good use, and they can be used to make plastics. So there is a reason for all of these reactions. It actually provides a purpose, not just because CIE want to give you an equation to learn. There's a reason for this, and if you're kind of going to develop chemistry a bit further and go into research or go to university or anything like that, then you might come across some of these and understanding the kind of concepts of it. So for non-primary alcohol chains, non-primary alcohol chains longer than 3 carbons, you can get different positional isomers. So you might get a bit of cis-trans isomerism. So obviously these are your stereoisomers that you would have seen in the previous topic. I'm trying to remember which topic it is. I think it's topic 13, I believe. You might want to double check that. It's the one where you do bonding and structure and bonding. If you're not comfortable with that, I urge you to go back and look through that video again, because there's loads of different types of isomerism. But anyway, for the purposes of this, just be aware that you may get cis-trans isomerism, so just be aware of that. Okay, so let's look at another reaction. This is obviously the dehydration of non-primary alcohols can lead to 3 different types of alkenes, and we'll go through these obviously systematically on here. So these are obviously elimination. You probably would have seen this word before. You definitely would have done into the introduction to organic AS chemistry. So I kind of went through it on there a bit, but elimination is obviously just to remove something from it, and obviously you must have a double bond that's produced. If you're going to remove atoms from a molecule, you've got to have a double bond to kind of cater for the fact that you've removed atoms from it. So basically, the double bond can be formed either side of the carbon that did have the hydroxyl group on it, so the OH group. So you'll see you've got the OH group here. Now the double bond can either form on one side or it can form on the other, and this is why you get 2 different products. So let's have a look on here. So you've got your OH group, which is there, okay, and you can add sulfuric acid and you form a double bond on the left-hand side, and that's where the OH would have been, or it can form on the right-hand side, and that's where the OH would have been there as well. So with this particular molecule here, this is where you might get your cis and trans, or also known as E and Z, because this one has a double bond. If we draw it in a particular way, you can either have the methyl groups all on the top side here. So this would be Z-butene, or also known as cis-butene as well. Or you can have them opposite the double bond and have it as E-butene or trans-butene. So you can effectively make, obviously, this version here, which is butanene. You can form Z-butene, and you can form E-butene. So you can form these 2 isomers here. Now, the reason why this can occur is because you have 2 different groups. There we are. on the one of the carbons on one side of the double bond, and that's what immediately should trigger you to think, right, I need to look at some cis and trans isomers. With this one, it doesn't have that, because obviously on this double bond here, you've got two hydrogens attached to the same carbon on this side, and you've got a hydrogen and C2H5 on the other side. So because these two are the same, you don't get any cis or trans with this one, but you will with this. So that's what you're looking out for, is anything where you've got a carbon and it's got two groups coming off that carbon, then that's where you could have cis and trans. So look out for them. Okay, so alcohols, they also react with sodium. Alcohols react with a lot of things, to be fair. But alcohols react with sodium to form a salt and some hydrogen gas. So sodium dissolves quite readily in alcohol, and we form this colourless solution. And when it's evaporated, what we do is we leave this white powder behind, this solid powder. And we will see fizzing that's observed. Now, you might have seen something similar with sodium when you just add it to water, so which is similar to alcohols. When you add sodium to water, you put it in a big glass container and it fizzes round, and it catches fire actually in water. And it goes like this orange, you get this nice orange flame and it turns into a ball. So you might have seen that in a lab. Alcohol is very similar in terms of how it reacts with water. It produces hydrogen gas, just like it does with water, except this one actually dissolves. And now we can evaporate that, and we get that solid white powder. Now the powder remains after evaporation. That powder is actually sodium alkoxide. And for example, if ethanol is used, then it would be sodium ethoxide that would be used. So it depends on obviously what your alcohol is that's being used. So the reaction, you've got your alcohol there. This is, in this case, is ethanol reacting with sodium, and that will form your sodium ethoxide, which is this one here, and hydrogen gas is produced. We can test this hydrogen gas with a lighted splint, and you should get a squeaky pop to demonstrate that hydrogen has been produced. Now, this ethoxide ion is a strong base, this bit here, so the reaction can be used to test for alcohols as well. So that's a way in which you can test for alcohols using this method. Okay, so let's look at the combustion of alcohols. This is probably the fun bit. Alcohols are incredibly flammable, just like alkanes are, and alkenes to an extent. But alcohols are definitely flammable. They're definitely used as a fuel. And we can use alcohols or burn alcohols to generate energy. So they burn readily. They have a lovely light blue flame. They're not smoky. Generally don't tend to be as smoky as alkanes. So especially shorter chain alcohols, they've generally got a very colourless flame. You really should keep if you've got alcohols like alcohol gels, for example, just be careful with, if they're quite strong alcohol content, then they could ignite. You've got to be careful with that. But also just be aware that alcohol, say spirits, for example, in drinks, alcoholic drinks, particularly spirits, because they've got a higher percentage of alcohol, they're flammable as well. So when they burn, just like with any other fuel, they burn in oxygen, they produce carbon dioxide and water, and effectively the alcohol is being oxidized when it's being burnt. So here's the alcohol here. Obviously that reacts with oxygen, and it forms carbon dioxide and water. So this is very similar to just the combustion of an alkane, which you've seen before. So alcohols, obviously, they can be oxidized using a mild oxidizing agent like potassium dichromate as well. Obviously, this is a very destructive version of oxidizing an alcohol. Obviously, you get two products that's formed, but it's quite, as you generates a lot of heat. But you can have a little bit more control and use an oxidizing agent instead of literally just setting fire to it. Okay, so let's have a look at these types of reactions then. So this is another type of oxidation of alcohols, but we're not going to burn it this time. We're going to add a reagent in there to do a kind of similar job. So alcohols can be oxidized by using acidified potassium dichromate solution. Now it's a lovely color. It's a nice orange color. So it looks like it looks like orangeade or something, or like orange juice. So potassium dichromate, K2CR2O7. going to have to be familiar with that formula because you're going to see it quite a bit throughout chemistry, to be honest. It's a very common oxidizing agent. Now, it's a mild oxidizing agent, so is reduced itself, and it will turn from orange to green, and green is effectively Cr3+. So this is going from your Cr2O7 down to Cr3, so it's been reduced itself. Okay, so that's really, really important when we're looking at these reactions, and that's why we get this colour change. So if we look at primary alcohols can be oxidized to aldehydes, and then they can be oxidized further to carboxylic acids. So let's have a look. There's an aldehyde. Obviously, we know what a primary alcohol looks like. Aldehydes look like this. They've got this functional group at the end, and they end in al. So, for example, this one's 1, 2, 3. So that's propanal. Okay, that's basically the name of that one. And now aldehydes can be oxidized further to carboxylic acids, and carboxylic acids have this functional group at the end. So they're very similar to this, except they've got OH on the bottom here. And so this one is, again, 3 carbons. It's going to be propanoic acid, so you end it in oic acid. Okay, so primary alcohols can be oxidized to an aldehyde and then to a ketone. Your secondary alcohols, they can be oxidized as well, and they can be oxidized to form ketones. And ketones are very similar to aldehydes, just that the carbonyl group here, the C double bond O, is actually in a middle carbon. So whenever you've got that in a middle carbon, then it's a ketone. If it's on the end, on a terminal carbon like this, then it's an aldehyde, and that's how you can tell the difference. So this ketone here obviously ends in -one, so this is propanone, this one here, because you've got 3 carbons, so it's propanone for that one. So tertiary alcohols, they can't be oxidized using dichromate. You can oxidize tertiary alcohols by burning them, as we've just seen before, but you can't actually oxidize them using dichromate, so that makes it nice and straightforward. Okay, so what practically do we do here? How do we actually do this? So we use 2 types of equipment. We use distillation and reflux, and both can be used to oxidize alcohols, but both have a particular purpose. So primary alcohols are oxidized, but the products produced are dependent on the method that we use when we oxidize it in the first place. And we're going to represent the oxidizing agent, and you'll see this quite a bit in chemistry as well, with a square bracket and an O in a square bracket, and that's just symbolizes an oxidizing agent that's being used. So let's have a look at this one. So this is a primary alcohol, and we are going to oxidize this, and we're going to form the aldehyde. Remember, that's what we've seen before. So the oxidation of primary alcohols, this produces the aldehyde and then the carboxylic acid. It's really difficult, though, to just extract this. If you want this, it's really difficult to do that if you're just heating this in a boiling tube, which you really shouldn't be doing anyway, to be honest, because this is incredibly flammable, but it's really difficult to extract. So if we want the aldehyde, then what we have to do is remove it at a certain point. And so for this reason, we use distillation. Okay, so distillation is where you've got your round bottom flask, you're heating it up, and you've got your Liebig condenser that kind of drops diagonally down to another vessel further along the line. And effectively, you're heating it up at a specific temperature. Some of the aldehyde will vaporize, go into the condenser, cool down, and you'll collect your aldehyde in the beaker separately. So it's a very controlled method, but you're extracting the aldehyde before it gets a chance to react further and form into a carboxylic acid. Now, if you did oxidize it further, let's assume, right, you don't really want the aldehyde, you just want the carboxylic acid. Then what we do is you don't have to worry about extracting this. You just set up a reflux setup like this. So you put some heat under there, water bath, because obviously it's flammable. You put your alcohol and your dichromate in there, you heat it up, and then what happens is it'll rise up the condenser, cool, and drop back down. It'll react again, and it'll basically go around in a circle like this. Every time it goes back in here, the aldehyde will have a chance to oxidize further to form your carboxylic acid. So what you should have left in here is carboxylic acid. That's what you should have. And we use excess oxidizing agent just to make sure we get everything, we mop everything up. So reflux, the advantage of reflux is it allows you to heat something strongly without actually losing any of your product. If you didn't have a reflux condenser and you just heated that up, all of your product would just escape into the atmosphere, and that's just no good. So you want to heat this up, condense it, and trap it back down into here, and that's why we use this this condenser here. And obviously that's filled with water in the kind of outer. It's kind of like a tube, and then you've got an inner tube, and then you've got water kind of flushing around the tube there to cool it down. Okay, secondary alcohols. Obviously, we can use these to make ketones, as I mentioned before. Now, it's difficult to oxidize ketones further, so it's quite straightforward reaction, this one. And again, we'll represent the oxidizing agent as O in the square bracket. So there's your secondary alcohol. Now, with this one, we just use reflux. There's nothing to separate. There's no kind of middle product to separate if we wanted to. So we just put secondary alcohol in there, put your dichromate in there, get it heated up, and then what you'll get is you'll produce your ketone. Now, your ketone won't oxidize any further, so you don't really have to be too kind of careful with this one. You just heat it up, give it a few minutes, and then you should have a lovely flask of ketone that's been produced in here. So with that one, you just go straight to reflux. Nice and straightforward. Okay, so another reaction of alcohols, it's kind of linked with the carboxylic acids that we've just seen there before, is we can react the carboxylic acids produced. We can also do it with anhydrides as well, but anhydrides is going to be kind of later in year 2. It's just another form of, once again, it's similar to a carboxylic acid, but you just need to know about carboxylic acids. They can be used to make esters, and you'll be a little bit more on esters later on in this, later on in the topic. Not this topic, but future topics, you know what I mean. So an ester is produced when we react carboxylic acid with an alcohol and sulfuric acid catalyst. So here's your carboxylic acid here, as you can probably see. That's reacting with the alcohol with an acid catalyst, and that'll form your ester. That's an ester there, and water. And you'll see a little bit more on esters later on. Esters are quite smelly. Some are good, some are bad. Some will smell like albus oil, like oil of wintergreen. Some will smell of pear drops. Some will smell of strawberries and raspberries. So it's vastly used. These chemicals here are used quite often in the food industry. Some of them are not so nice. You get one which smells like rancid butter, which you definitely don't want. So yeah, so there'll be a little bit more on that in later topics. Okay, and the final reaction that you should be aware of as well is that when we react hydroxyl groups or you have hydroxyl groups which have a methyl group attached, they can actually react with iodine, and we call this an iodoform reaction. This is a lovely reaction because you get lovely bright colours formed from this, and it's not often in organic chemistry that you get lovely bright colours. Normally that's reserved for inorganic chemistry, which is transition metals and all of that. So if we heat iodine in the presence of an alkali with methyl hydroxyl group present, then we'll produce a yellow precipitate. It's bright yellow, and it's called triiodomethane, so it's CHI3. Okay, now this only happens strictly under certain reactions. So a methyl hydroxyl group only exists in these two circumstances. So it's quite a unique reaction. So in ethanol, so this is ethanol, this reaction here, and you can see we've got an OH group bonded to a carbon, which is then bonded to a CH3. Okay, so that's when that can happen. Or in this type of secondary alcohol. So in other words, the OH group is bonded to the carbon with a CH3 at the end, okay, and then this R can be any carbon chain length whatsoever. So if you have these two scenarios here, any one of these chemicals, watch out for them in the exam. If they give you something like this and you're reacting it with iodine in the presence of an alkali, then you will get these products here. So just keep your kind of eyes open for these type of chemicals and just think, okay, I could be producing some of these products here. So yeah, really important. Right, and that's it. So that is everything you need to know for the hydroxy compounds for topic 16. Like I said, there's a full range of A-level videos, year 1 and year 2 for the CIE specification. Please hit the subscribe button to show your support. That'll be brilliant. And again, these slides are available to purchase. They're really good value for money. You can use them as part of your revision, and use them as part of your notes, etc. If you click on the link in the description box below, you can get a hold of them there. Again, the full range of A-level resources are there too. But that's it. I hope that was helpful. Bye bye.